All right, guys, welcome to Honors Chemistry. We are going to continue our foray into periodic trends. Today we're going to talk about ionization energy. Now, we haven't really talked about ions too much. Ions are atoms where the number of protons do not equal the number of electrons, so they obviously have a charge. So sometimes we will have some extra electrons, which will mean that we will have a negative charge. Sometimes we might have a few extra protons compared to the electrons, which means we will have a positive charge. So when we talk about ionization energy, we're going to talk about forming positive ions. Okay? So in order to form a positive ion, I have to remove an electron from a neutral atom. Usually the electron that we remove is from the valence shell or the outermost shell of that atom. So we remove that electron from the neutral atom, and it takes some energy to do that. The energy needed to overcome the attraction between the positive charge of the nucleus and the outer electron is called the ionization energy. Specifically, that ionization energy is pulling an electron, a valence electron, off of a neutral atom in the gaseous state. So we're doing it from the gaseous atom, the gaseous state. So I want you to think of the ionization energy as an indication of how well an atom is able to, that nucleus is able to handle or hold on to its valence electrons. Okay, the more ionization energy that we have to spend to get that electron removed, the more that nucleus is able to hold on to that electron. A high ionization energy value indicates that an atom has a strong hold on its electrons, and atoms with large ionization values are less likely to form positive ions. Okay. So if I have a really large ionization energy, I'm not going to form positive ions. By and large, I'm going to be forming negative ions. Likewise, if I have a really low ionization energy, meaning that it's really easy for me to take that electron and pull it away from the atom, it's going to be very easy to pull that electron off and make a positive ion. So low ionization energy values that an atom loses outer electrons pretty easily, and such atoms are very likely to form positive ions. So let's look at our trend here. Now I want you to look at each of these lines. So we don't really have we do have things for each period. So here we have period 1, we have hydrogen to helium. We have period 2 in this group, lithium to neon, and period 3. So remember, the periods are the lines that go across the periodic table. They are the rows. So we are going from left to right across these rows. And notice as we go from left to right, each of these rows, the ionization energy increases. Okay? So what we can say is as we travel from left to right across the periodic table, our ionization energy tends to go up and up and up. Okay? So let's look at this also. Let's look at it in terms of let's look at the first column on the periodic table. So this group, we got hydrogen, lithium, sodium, potassium, rubidium. Notice as we go down this group, our ionization energy gets a little bit less each time. And let's look at the noble gases. This is another group. Helium, neon, argon, krypton, and xenon. Notice as we go down that group, our ionization energy also goes down. Okay? So if we look at the periodic table, our ionization energy goes down. So this decreases as we go down the periodic table, and it also decreases as we go from right to left. So the normal trend for ionization energy, we usually do trends in terms of increasing. Let's change the color here. The trend is, this is the largest. So the atoms or the elements at the upper right-hand corner of the periodic table will have the highest ionization energy, and the atoms here on the lower left will have the smallest ionization energy. So these atoms up in the upper right-hand corner are very difficult to pull electrons away from. These atoms in the lower left-hand corner are very easy to pull electrons away from. Okay? So I want to ask you a question here. Why do you think the noble gases, helium, neon, krypton, argon, xenon, why do they have such high ionization energies? And don't think of the phrase because they're super stable. Think about size. We're pulling an electron away. I'll give you a second to think about that. Okay, don't you think as we travel across the periodic table to the noble gas column or group, doesn't our atomic size go down? Our atomic radius goes down as we travel to that noble gas group. And if we look at the electrons in those noble gases, that is where the electrons are the closest to the nucleus in each period. And isn't it going to be harder to pull an electron away the closer it is to the nucleus? Remember, the nucleus is where the positives are. Electrons are negatives. They attract each other. So if the noble gases are where the electrons are closest to the nucleus, it also is going to have the best attraction between the nucleus and the electron, pulling them in. So the noble gases have the smallest atomic radii of their period, meaning electrons are closest to the nucleus in noble gases. Also meaning, do you guys know that 3 little dots mean therefore? This is kind of shorthand for therefore. Therefore, the electrons are the most attracted to the nucleus in noble gases. Therefore, hardest atom of a period to ionize will be noble gases. Okay? All right, I'll give you a minute to write that all down. So just because the radius is the smallest, that means the electrons are the closest to the nucleus, therefore they are the most attracted to the nucleus when we get to the noble gases, meaning they're the hardest to pull away. That means the noble gases are the hardest to ionize in any group. Okay, why do you think the alkali metals have such a low ionization energy? Think about that. Think about atomic size again. Aren't the alkali metals the largest in their period? So if they're the largest, doesn't it mean that the electrons are going to be the farthest away, meaning they're going to be the easiest to pull off? Yep. So alkali metals have the largest radii. Of their period. Period. I can't spell. Meaning electrons are not super attracted to the nucleus. And easy to pull away. Okay, so those electrons are not super attracted to the nucleus because they're pretty far out there in terms of radius, which means that they're easier to pull away and make an ion. So let's look at which element has the smaller radius. So we're going to look at lithium and nitrogen. So I'm going to grab a periodic table and we're going to look at lithium and we're going to look at nitrogen. Okay, so I want to highlight lithium and I want to highlight nitrogen. If I can get a drawing. So lithium and nitrogen. Which one is larger? Which one is smaller? Remember our trend of size. Our trend of size is we get smaller going this way, and we get smaller going this way. So which one's going to be smaller? If you said nitrogen, you are correct. So nitrogen is smaller. I want you to look at krypton and neon and look at cesium and lithium and take a guess. You guys ready to check? Okay, krypton and neon. Let's look at that. Krypton and neon. Neon's right here, krypton's here. Okay, remember our trend is to get smaller as we go to the top. So neon would be smaller. And then last but not least, cesium and lithium. Let's look at that. So cesium and lithium again. Once again, remember our trend is to get smaller as we go to the top. So lithium will be smaller. Okay, now let's look at this. Which element has the larger ionization energy? No, it doesn't want me to move my circles. So ionization energy, remember ionization energy is exactly the opposite of size. When the size gets larger, the ionization energy gets smaller. So which element has the larger ionization energy? Let's look at lithium and nitrogen first. So once again, lithium and nitrogen. Let's change the color. No, it doesn't want to change the color. So lithium and nitrogen. Remember, ionization energy trend is the opposite. And this time we're looking for larger, not smaller, but larger. So because it's the opposite and we're looking for the opposite thing, we're looking for larger, nitrogen has the larger ionization energy. So let's highlight nitrogen. Okay, I want you guys to look at krypton and neon and cesium and lithium as well. Okay, so take a minute and look at those. Okay, did you get the same answers as above? So between krypton and neon, remember ionization energy gets larger as we go up. So if we're going to look at krypton and neon is higher up on the periodic table. So neon will have a larger ionization energy. And if we look at cesium and lithium, same thing. Cesium's down here, lithium's up here. So lithium's higher on the periodic table, so it will have a higher energy or a higher ionization energy. So lithium we would choose as well to have the larger or the higher ionization energy. So let's explain how atomic radius and ionization energy are related to each other really quick. Okay? Well, so as atomic radius increases, ionization energy decreases. So they are inverse. They are related inversely. So as one gets larger, the other gets smaller. So this little alpha sign that I put here in the middle means related to. It usually means that I need to have some kind of a constant, but if one gets bigger, the other is going to get smaller. It's an inverse relationship. Okay, so let's look at some more stuff. Successive ionization energies. Excuse me.